Good morning, everyone. Today is December 22nd, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. And you can help support our mission at naturalphilosophy.org, where you can become a member or renew your membership. And we discuss things in our forums and our wikis. And we are also active in social media. Please find us and like us on Facebook, as well as YouTube, where you will find recordings of the science chats on our YouTube channel. And if you'd like to help out, we are organized through a website called Basecamp, hq.naturalphilosophy.org. And rules of conduct for this science chat is that we are to treat all other participants with respect and politeness, and discussion should be limited to the science topics. And please no personal attacks. And you can find all our rules on our website. As well, we would ask that you leave your camera off if you're not speaking, and to also mute your microphone. But if you are speaking, please go ahead and turn on your camera to help conserve bandwidth. And our upcoming conference is going to be this June 26th to 29th at the University of Washington. So we invite you to think about coming and presenting the conference. Our featured keynote speaker will be Dr. Gerald Pollack. Okay, so this week we have Lori Gardia.
It's actually Gardi, but David says Gardi, and I like that. So you can call me Lori Gardi. It sounds more French.
Oui. Okay. Oui. So we have you presented today on the nature of light. So I'll let you go. Go ahead.
Okay, so is everything good? I'm hearing an echo.
And your presentation, get that started.
Okay. So I can go. I'm good to go.
Let's see if someone is.
Yeah, I'm hearing an echo from somewhere.
Let's fix that. So Robert French, if you could turn off your video, that would help us. Thank you.
That should work. Okay, so welcome everyone to the Saturday morning science chat. I'm really honored to be here to do a little presentation for you. So what I've done is I pre-recorded a slide presentation just because I'm a little nervous about giving public talks. I'm not really good at it. So, and it's really, what I'm saying today, I believe is really important. I need to say it in just the right way, with the right wording and the right order. I want you to follow my train of thought. And the other good reason for pre-recording my slides is no one can interrupt me. So the presentation is going to be around 40 minutes, a little bit more than 40 minutes. And then when it's done, I will be open for questions. So I'm going to start the show and then just make sure that everything is working fine. So
you can start by sharing your screen.
Okay, so I haven't shared my screen yet, so good. I need to do that. Share my screen. That one. All right, so
I can see all the fractals in your office.
Yeah, I got lots of them. So I'm going to start the show, and then you know, we'll talk in around 40 minutes or so. If anything goes wrong, though, let me know.
Photons even exist? Is light a wave? Is it a particle? Is it something completely different? Is it all of the above? What is light? Can it even be defined? There are a lot of questions surrounding the nature of light.
there a way to turn up the volume? It's hard to hear.
Is it?
Oh, you re-recorded the volume as well? Yeah, we can't hear you from the presentation.
Okay, let me turn my volume up if I can. Play. Okay, yeah, I can turn mine up. All right, I'll continue.
Planck's energy equation is at the heart of all these questions.
Yeah, that's still pretty quiet.
That's all I can do. That's all I can do.
Sorry, let's see. Do you have a headphone or something? So is the sound coming out of your computer is where it's coming from?
Yeah, this is how I recorded it.
Because if you have a microphone or something, you should put the microphone right next to the speaker. That would help us.
Oh, okay. Let me try that. It might feed back though. Okay, let's try that. See if this works better. Oh. So it's really, really low, like you can't hear it at all?
Just about.
Just about. Okay. I'm not really sure what to do here.
Well, you're speaking through the microphone and your headset, right?
Yeah.
Take your headset, microphone, and put it right next to your computer speaker.
Well, I turned the speaker off, though.
Now you want to turn your speaker on and then
Okay.
put your headset right next to it.
Okay.
And you'll want to monitor the chat so that we'll still be able to communicate with you if something happens.
Okay. So
like open up the chat window.
Yeah, I just have to change my so my speaker's on. I need to change my to the speaker. Turn this off. Shoot.
Yeah, this is one of those little complications there. Sometimes, like if I show a video, the audio of the video won't come out to the audience.
Right. I just can't, it won't let me select my speaker. Set default. Okay, I can change it now there. Let's try that.
Planck's energy equation is at the heart of all these questions.
Okay, that works.
Is that better?
Is extremely
yeah, that's much better. If you do that.
Understanding of the nature of light.
Is that okay? I'll just start over and we can cut out that part maybe.
Okay, I think we're good then.
The main focus of my research is to try to understand the nature of light. Everything I do, every paper I write, is in an effort to try to understand light. What is light? What is a photon? Do photons even exist? Is light a wave? Is it a particle? Is it something completely different? Is it all of the above? What is light? Can it even be defined? There are a lot of questions surrounding the nature of light. Planck's energy equation is at the heart of all these questions. A proper understanding of this equation is extremely important in the understanding of the nature of light and quantum mechanics. No one really understands quantum mechanics, according to Richard Feynman. Well, I'm not satisfied with not understanding. I want to understand. My gut feeling is that something is terribly wrong in the standard interpretation of this energy equation. As a computer scientist, I'm pretty good at finding bugs. At work, if someone can't find a bug in their program, they often come to me. So I felt that there was a bug in the current interpretation of Planck's energy equation. And so I took this as a challenge to myself to find the bug and then fix it. So this became my quest. In the end, I did find the bug. And it's not a small bug. It's a huge dragon-sized bug, one that should not be ignored.
Am I overstating my claims? Well, I guess that's up to you to decide. A little bit about me. My name is Lori Gardi. I'm a computer scientist, and I work in the field of medical imaging. My area of expertise is 3D ultrasound, and so I'm very familiar with the physics of ultrasound. For example, it is my understanding that ultrasound waves can be both longitudinal and transverse. So when people say that light can't be a sound wave because light is transverse, I beg to differ. Sound waves can be transverse. Solids can transmit sound waves. And it was recently discovered that superfluids can transmit transverse waves too. Although I don't have a PhD, I have helped dozens of kids get their masters and PhDs. And I've co-authored many papers and even a few that I've written on my own. All of my papers are on ResearchGate, so if you want to check them out, they're pretty easy to find. So enough about me. This guy here is the star of the show. This equation, in my humble opinion, is the source of all the confusion surrounding light. This equation, in my humble opinion, is the source of all the problems with quantum mechanics. And this tiny equation, in my humble opinion, might even be the source of all the problems, confusions, and misinterpretations regarding the origin and evolution of the universe itself. I believe there's a bug in the program. The bug! This is a clue. The bug is over here. Before we get into this, I want to look at the other energy equation, E equals mc squared. When I study physics, I pay a lot of attention to unit analysis. Unit analysis is my thing. I wasn't happy with the current implementation of unit analysis, or dimensional analysis as they call it, and so I developed my own. I call it modified unit analysis. Modified unit analysis is almost exactly the same as standard unit analysis, with one simple addition, which I will show you. So, what are the units for this equation? The unit of energy is the joule, the unit of mass is the kilogram, and c squared interprets as emission and absorption. As you can see, this unit equation is an expression of the units of the joule. Notice that every term in the body of the equation has a corresponding unit in the unit section. This is how unit analysis works. Unit analysis is very important. The best way to find a flaw in an equation or a system of equations is to write down the units. If the units don't balance, then for sure something is wrong. Unit analysis also helps with interpretation. You can hide things in equations, but unit analysis, if done correctly, tells the whole story. So modified unit analysis puts square brackets around the unit terms to distinguish them from the terms in the body of the equation. Notice that there's an m in the body of the equation and there's an m in the unit section. In the body of the equation, m means mass, and in the unit section, m means the meter. So the square brackets are a very important notation because they help resolve this ambiguity. Now let's compare these two energy equations. Both of these equations have a variable, F and m. Both of these equations have a constant, h and c squared. And both of these equations equate to energy, E. In fact, written this way, you might think that you can equate these two equations like this. In practice, I have seen this done. But does it really make sense to do this? So a few years back, when I was studying this equation, I thought it would be interesting to sit in on an MRI class. Since I work in the field of medical imaging and I was working with MRI images at the time, I thought it would be prudent to learn more about MRI physics. Interestingly, this equation appeared in one of the very first slides of the very first class. Only it wasn't written like this. It was written like this. In MRI physics, this is how they write this equation. Delta E stands for change in energy. This important detail actually helped me find the bug. Technically, these two equations cannot be equated. These expressions are talking about two different things. The one on the left is about energy transformation, mass to energy, and vice versa. The one on the right is about energy transmission, the transmission of light energy. Energy transformation is instantaneous. It needs no time parameter. Energy transmission takes time. This delta implies that Planck's energy equation is the equation of an experiment. Experiments take time. In order to see the difference, we need to study the units. As we saw before, E equals mc squared has the units of the joule. Planck's energy equation has the same units, plus some extra stuff, and this must also evaluate to the joule. These are the units normally associated with Planck's constant. They call it the action constant. And these are the standard units for frequency or hertz, which literally translates to cycles per second. All of these units must simplify to the unit of the joule. Can you see the bug? The bug! So what is the problem? These units evaluate to joule. But what about the extra stuff? Here, the s's cancel and you end up with a 1, and j times 1 equals j, right? This is not true in the unit section of an equation. I agree that in the body of an equation, this is true. For example, k times 1 equals k. If that was in the body of the equation, it would be true. But this is not true in the unit section of an equation. Units are not numbers. They are placeholders for numbers. This is why the unit for time is s, and the unit for space is m, and the unit for mass is kg for kilogram. When the unit for frequency was defined as 1 over s, it gives the false impression that the 1 in this expression is the numerical value of 1. It's not. The 1 in the units of frequency stands for 1 cycle. This little 1 cannot operate on anyone, nor can it be operated on. Like all other units, like S and M and kg, the 1 in the unit of frequency is a placeholder for a numerical value. It is a character, not the numerical value of 1. Thus, this is not true in the unit section of an equation. There is no place for numerical values in unit analysis, not even the numerical value of 1. It is a mistake to do this. This is where I found the bug. This is the bug. The bug! Now that we've identified the bug, I'm going to show you how to fix it. Then I'm going to show you how fixing the bug leads to a better understanding of the nature of light. Spoiler alert, photons as defined by mainstream physics do not exist. Next, I'm going to teach you about modified unit analysis. Standard unit analysis is often referred to as dimensional analysis, but modified unit analysis calls it domain analysis. The domain of time has the units s for second. The domain of space has the units of m for meter. The domain of mass, or inertia, has the unit kg for kilogram. And the domain of charge has the units C for coulomb. So far, nothing changes from standard dimensional analysis. Modified unit analysis adds another domain to the domain of units, which I refer to as the domain of oscillation, or simply the domain of cycles. The symbol given to the unit for this domain is the delta symbol and interprets as 1 cycle. Using a symbol instead of the numerical value of 1 is going to help us identify and fix the bug. Since modified unit analysis adds the domain of oscillation to the language of unit analysis, all of the units that belong to the domain of oscillation need to be rewritten. In modified unit analysis, the units for frequency are written like this: cycles per second. The unit for wavelength is written like this: meters per cycle. The unit for time period is written like this: seconds per cycle. And the unit for the wave number is written like this: cycles per meter. This is really the only change that modified unit analysis is making to the standard approach. So what does this buy us? Let's go back to Planck's energy equation, only this time we're going to write the units using modified unit analysis. Writing it this way makes it obvious that the units do not balance. The units do not evaluate to exactly the joule. This, in my opinion, is, if this is in fact a bug, then how do we fix it? In order to get the units of this equation to evaluate to exactly J, or the joule, we need to add another delta term or cycle term to the unit section. Now we can clearly see that the units of the time period are buried in the unit section of the equation. The units, written like this, look beautiful to me. They are nicely balanced, and the result equates to J as required without using any mathematical trickery. And there are no numerical values in the unit section as required by modified unit analysis. Numerical values have no value in the unit section of an equation. This includes the numerical value of 1. This is an important point that I can't overstate. Since modified unit analysis disallows numerical values in the unit section of an equation, this is the only way to balance the unit section of Planck's energy equation. So how do we interpret this? First of all, this is the real action constant here. Written this way, Planck's constant interprets as the energy of one period of a light wave. Of means times in arithmetic. So written this way, Planck's constant interprets as the energy of one period of a light wave. If light is a wave, then Planck's constant is the energy of one period, one cycle, and or one wavelength of a light wave. In other words, no matter which frequency you are talking about, each period of light contains the same energy. Every wavelength of light contains the same energy. Okay, so let's go back to the original units and do this another way. Here, we're only looking at the units. J times S are the standard units of action, and 1 over S are the standard units of frequency. Divide both sides by S, and now I'm going to write the equation for these units. I have now transformed Planck's energy equation into a power equation. It actually makes more sense to write this equation in terms of power, since the original Blackbody experiments were reported in terms of power. The original Blackbody experiments are plotting wavelength against intensity. The intensity of light increases with shorter wavelength, not the energy. Intensity has units of power per meter squared, or watts per meter squared. Here are the units written in terms of energy. The units of power are joules per second. The units of intensity are the key to understanding the relationship between wavelength and energy. Without rigorous unit analysis, this is very difficult to see. Why the Blackbody equation wasn't written in terms of power in the first place is a mystery to me, but I think it has something to do with this word period, which makes some people really uncomfortable for some reason. Okay, now we're going to look at this one more way. Here is the power equation from a previous slide. Now I'm going to convert it back to an energy equation. Step 1. This exposes the missing measure time parameter. This is the measure time parameter of the experiment. Power delivery requires time. Step 2. Multiply both sides by t. Now we can see that the anomalous unit of time that was previously assigned to the action constant actually belongs to a previously hidden measure time parameter in the body of the equation. As I said before, this equation is the equation of an experiment. This belongs to this. So what happened? It turns out that this previously hidden measure time parameter, which was apparently in the original writings of Planck himself, was inadvertently hard-coded to the numerical value of 1 and subsequently buried because you don't need to write 1 in the body of an equation. We have just found another bug. The bug! So where does this leave us? It makes more sense to write the equation in terms of power, since the Blackbody experiments were originally reported in terms of intensity, which is power per meter squared. But if you want to write it in terms of energy, then you have to use modified unit analysis. Otherwise, the units don't balance. Now that the unit section is balanced, we need to look one more time at the body of the equation. As I said earlier, things can be hidden in equations. This is done to make them look more elegant. But as a computer scientist, I don't want elegant. I want completeness. I want to make sure that I can see all the parameters so I can write a computer program that makes logical sense. Here is what we have so far. But there are still a lot of things hidden in this equation. For example, there is something hidden in the frequency term. In the body of an equation, frequency stands for cycles per measure time. Here, n is the number of cycles and t is the duration of time or time interval. Frequency is equal to n counts per measure time. Measure time can be anything. Yes, I agree that the unit of frequency is cycles per second, But a frequency term in the body of an equation can be associated with any time interval. For example, an adult woman gets her period approximately once per month. So frequency in this case is approximately 12 cycles per year. Here, N is 12 and T is 1 year. Frequency in the body of an equation need not be cycles per second. So this raises an important point. When we plug an actual frequency into Planck's energy equation, are we not hard coding the measure time to exactly 1 second? For example, a gamma ray oscillates at around 10 to the 19 times per second. When we plug 10 to the 19 into Planck's energy equation, are we not calculating the energy transmitted in a 1 second time interval? Otherwise, what does cycles per second mean? Just think about it. Okay, so now we can write this. Next, we are going to multiply the top and bottom by 2 pi. Why? Because in the domain of oscillation, 2 pi corresponds to 1 cycle. And since the equation contains a frequency term, I wanted to show where cycle fits into the body of this equation. Then we arrange and write the following. Here, h over 2 pi is reduced Planck's constant, and the term on the right corresponds to angular frequency. Written this way, it's clear to see that measure time t in the body of the equation was historically hard-coded to exactly 1 second. In case this isn't clear, let's look at it again. The only time you do not have to write a value into the body of an equation is when it is equal to 1. In other words, frequency in Planck's energy equation is cycles per second and not cycles per measure time. Planck's energy equation is the equation of an experiment with a duration of exactly 1 second. The photon, E, in Planck's equation is the energy of 1 second's worth of Planck energy units. E is not and cannot be fundamental. Finally, the picture is complete. Notice that every parameter in the body of the equation has a corresponding unit in the unit section. Also notice that each 2 pi in the body of the equation has a corresponding delta in the unit section. So what does this buy us? Modified unit analysis, as described in the previous slides, has huge implications with regard to the uncertainty principle. The 2 main expressions involved in the uncertainty principle look like this. The historical interpretation of these 2 inequalities seems a bit strange. In quantum mechanics, there exists a fundamental limit with which certain pairs of physical properties of a particle can be known. For example, the position of a particle and its momentum cannot be simultaneously known. Modified unit analysis has a different interpretation of these inequalities. In fact, MUA takes the uncertainty out of the uncertainty principle. Here's how that works. Let's look at the second one first. Previously, I showed how the measure time parameter for Planck's energy equation was set equal to 1 and subsequently hidden. For completeness, modified unit analysis decouples the time parameter from the action constant and explicitly writes it in the equation. The uncertainty relation is written like this. Here, H is given a different label, HQ, even though it has the exact same numerical value as Planck's constant. but it no longer carries the extra unit of S. HQ interprets as quantum of energy. This relation now simplifies to this. The interpretation of this is quite simple. A change in energy less than the quantum of energy can never be created or detected. All detectable energy changes will be greater than or equal to the quantum of energy. It can't get much simpler than this. We will never be able to detect an energy transition or energy change smaller than Planck's constant. We can now make a prediction. If the minimal detectable energy is quantum of energy, or HQ, then this must correspond to a minimum detectable temperature. The units of Boltzmann constant are joules per Kelvin. This is a conversion factor. In order to convert energy to temperature, we must divide energy by Boltzmann's constant. If we plug in the quantum of energy into this equation, according to MUA, this should give us the minimum detectable temperature. The only temperature smaller than this, according to MUA, is 0. So what is the lowest temperature ever created and measured? If a temperature lower than this was ever measured, then this would falsify the quantum of energy as the smallest detectable energy. So far, the coldest temperature ever created was by a group at MIT who created and measured a temperature of around 500 picokelvin, or 5 times 10 to the minus 10 Kelvin. This is only one order of magnitude higher than the quantum of temperature predicted by modified unit analysis. So the quantum of temperature has not yet been falsified. So far, so good. Now, we're going to do the same thing with the other inequality. Like in the previous example, we have decoupled the time parameter from the action constant and placed it into the expression beside the quantum of energy. And now we divide both sides by delta T. Delta P is momentum, delta X over delta T is velocity. So the expression on the left here has the units of energy. And so we're back to this relation. A change in energy less than the quantum of energy can never be created, nor can it be detected, no matter what frequency of light we are talking about. Put simply, all frequencies of light are quantized by Planck's constant. But how? In modified unit analysis, there can be only one explanation. Every period of light carries the same energy, the quantum of energy. This shocking interpretation of light is contrary to what is currently said about light. Currently, we say that every wavelength of light corresponds to a different amount of energy. But what modified unit analysis seems to be saying is that every wavelength of light carries the same energy. And we're back to what? Traditionally, photons are defined as fundamental particles of light, and the output of this equation is said to be the energy of one photon. At least that is what I was taught, and this is what people are saying. Electrons are fundamental particles because all electrons have the same mass. Protons are fundamental particles because all protons have the same mass. But the output of this equation, E, can take on many values. It's a variable. The output of this equation, which is a variable, cannot be fundamental. On the other hand, modified unit analysis seems to be saying that Planck's constant is fundamental. Planck's constant is the fundamental quantum of energy. Doesn't it make more sense to call the fundamental thing the photon and not the variable thing? It is my opinion, based on my research, that defining the photon as a fundamental particle was a mistake in interpretation. This happened because the term cycle was inadvertently removed from the language of unit analysis and replaced by the numerical value of 1, which was a mathematical and logical mistake. Numerical values do not belong in the unit section of an equation, not even the numerical value of 1. What I'm saying here is that every wavelength of light carries the same energy no matter what frequency we are talking about. It is only the intensity of light that changes with wavelength. This is what the Blackbody experiments were telling us. So next, I'm going to show you how every wavelength of light can carry the same energy, and at the same time, a decrease in the wavelength can increase the intensity of the light received by a detector. So here is one of the main figures from my paper, Planck's constant and the nature of light. This is a schematic of 3 frequencies of light entering a detector. Here, the unit of time is exactly 1 second. In this schematic, each period of light carries the same quantum of energy. Each dot represents 1 quantum of energy. Keep in mind that this is just a schematic, and this is not what I think light looks like, okay? In the Blackbody curve, the maximum intensity increases with smaller wavelengths of light. Looking at the units for intensity, you see that there are several ways that this can happen. You can increase the number of energy quanta delivered in unit time. Clearly, the bottom one delivers more energy units per unit time, per second. Or you can deliver the same amount of energy to a smaller surface area of the detector in a shorter period of time. Clearly, the bottom one delivers the same amount of energy to a smaller area of the detector in a shorter period of time. This explains how every period of light can carry the same energy, but the intensity of the light can still increase with shorter wavelengths. It is the intensity of the light that changes with wavelength, not the energy. And, well, that's about it. Planck's constant is a quantum of energy. And the reason that all frequencies of light are quantized by this value is because all wavelengths of light contain the same amount of energy, a quantum of energy. Modified unit analysis led me to an alternate interpretation of light where every wavelength of light carries the same quantum of energy, but different wavelengths deliver different energy intensities to the detector. Although the units of intensity contain the units of energy, the units of intensity and the units of energy are not the same thing. Long story short, Planck's constant is the real fundamental, and it should have been given the name photon. The so-called photon of the standard model is E is not the energy of a fundamental particle. E can take on many values, so it cannot be fundamental. If E is not the energy of a photon, then what is it? Since the frequency term in Planck's energy equation is defined as cycles per second, then this equation must be the equation of a 1 second experiment. In modified unit analysis, E interprets as an arbitrary collection of 1 second's worth of energy quanta. Something went terribly wrong more than 100 years ago when Planck and the boys were trying to write this equation for the Blackbody experiment. The real quantum of energy is the real star of the show. The real quantum of energy is the real photon. Finally, what I'm going to do is compare and contrast the standard interpretation of light against the modified unit analysis interpretation. To do this, I'm going to use the famous lecture by Dr. Neil Turok called The Astonishing Simplicity of Everything. I attended this lecture, and so I thought it would be the perfect video to end this presentation with.
Now, having discovered that physics works through waves and through this back and forth motion described so nicely by the imaginary number, which, by the way, any electrical engineer will tell you they know I very well. It's a very useful trick. But having discovered all that, there was one huge problem. See, waves don't really make sense in the physical world. If Maxwell was right, was absolutely right, that light was a wave and that was the end of the story, none of the world we know would work. And the reason has to do with heat. Look at the sun. It's obviously very hot. It is shining at light at a certain wavelength, the wavelength of visible light, which is a fraction of a millionth of a meter, fraction of a micrometer. If waves really existed, as in Maxwell's theory, with no other caveats, the sun could not exist. For the following reason. You see, waves can carry energy. And the problem is that if you allow waves of arbitrary wavelength, you can fit an arbitrary number of those waves into any volume of space. Okay, so say we're sitting in this room, and I want to tell you about all the possible waves of the tiniest little wavelength you could imagine. How many waves could you fit in the room? Well, as many as you like, because I can make them as small as you like. Okay, because they're there, they're waves, they're solutions to Maxwell's equation. The trouble is, if there really was this infinity of possible short waves, they would carry the heat of the sun away in an instant. Okay, so if Maxwell was true, the sun couldn't exist. And it's true of any hot object. The only thing that saves the day is that light isn't a wave. Okay, it's a particle. And that's what Max Planck discovered in 1900. Planck was hired by the German Bureau of Standards to help design light bulbs that would be more efficient. They needed to emit the maximum possible amount of light in visible wavelengths. And so that was his task. And so he had to make a theory of why is it that a hot wire glows at a certain temperature or a certain wavelength. Hot wire of a certain temperature, why is there a corresponding wavelength? And the more he tried, the more confused he got. Nothing made any sense because he kept losing all the energy into infinitely short waves. There are just so many of them. And so he hit upon a simple idea that light refuses to carry energy except in packets which depend on the wavelength of the light. So the short wavelength light, the very little waves, are incredibly fussy. The energy they carry is huge. And basically it says, if you don't have enough energy for me to take, I'm not taking any. and that's the consequence of why the sun is stable. So if you want to know, so Planck's law was that the energy light carries is a new constant of nature called Planck's constant times the frequency of the light. Frequency is higher the shorter the wavelength.
Neil Turok is the dragon in my story, not only because he's freakishly tall, but because he's a big figure in theoretical physics. He is the director of the world-famous Perimeter Institute of Theoretical Physics. I'm no one compared to him. I'm David, and he's Goliath. I'm just a little bug compared to him. Neil Turok has a huge responsibility. The people in that audience are looking to him for answers to the mysteries of the universe, and that is a tall order. So this is what I'm up against. If I'm right about what I'm saying here, then something needs to be done. If I'm right, then part of the program needs to be rewritten. I'm not afraid to rewrite my programs from scratch. I've done it many times in my life. Fear of change is a handicap. I've met Dr. Turok several times, and I can tell that he's a great guy. So this isn't anything personal against him. I know that I'm not worthy to be even standing next to him, let alone telling him what to do. But I have an idea, and I think it's a good idea. And I would like to entertain this idea and see where it leads. But I can't do it on my own. I need a team. There are a lot of bugs still to fix. So if anyone is interested in being on my team, please let me know. Otherwise, I'm ready to take some questions. Okay. Are you still there? Shoot.
Yep, we're still here.
Oh, good.
Okay,
Excellent.
so thank you for your presentation.
You're
And,
welcome.
We're open for questions. If you have a question, you can raise your flag.
Hello?
Now, I don't see any immediate questions. So, but I was wondering about, like, what exactly is the relationship between Planck's constant and the Blackbody experiment? Those two things seem to be very different.
Well, I think the you can hear me, right?
Yeah,
Okay,
we
I
can
think.
hear you.
Okay, good. I think. Well, the Planck's constant was actually discovered because of the Blackbody experiments. Okay, so what they discovered when they did the Blackbody experiments is that all the energies that they were getting were, no matter what frequency they're talking about, were quantized by this Planck's constant. Okay, so let me just go. I'm just gonna.
Yeah, but that's the part I don't understand, because I see the graph they have for Blackbody radiation, and none of that is screaming that there's this quantization. All of that screaming is that you don't have a lot of frequency and a lot of power at the high frequencies, and it doesn't at all seem to follow.
Yeah, no, it's not clear from this diagram, obviously, but when they actually do the experiments and they plug in different frequencies and they analyze the intensities, and they take the temperature and divide it by the energy, or I can't really explain off the top of my head exactly what they did, but through the experimentation, they discovered that they kept getting this number kept popping out. Right. So you'd have to look at the actual experiments. I don't think I can explain it off the top of my head right now, like exactly what steps they took to get that value. But it's, I did run through that at one point in my life because I had the same question. So at one point I went through and did the math and it worked out. So it's pretty easy. You could probably look it up and find that out pretty easily. But doing it their way, it's very difficult to explain, because it doesn't make sense that if every wavelength of light carries a different amount of energy, then how can it possibly be quantized at the same time? So the way I do it, the way I look at it is, and you can still see my screen, right? The way I'm approaching it is that every wavelength of light carries the same energy. Now, I think they were just confused because the units of intensity contain the units of joule, and the units of joule are on top in the numerator. That they were thinking, oh, it must you know, every wavelength, the shorter wavelengths of light must carry more energy. But that it's really, really hard for me to, it was really, really hard for me to understand that. And you know, it doesn't make sense. And I think it's because every wavelength of light carries the same quantum of energy. It's just more energy units in the smaller wavelength can be delivered to the detector in the same amount of time. Or the same amount of energy can be delivered to the detector in a shorter period of time. It's like taking a hammer, and either you hammer it, when you hammer it fast, the intensity of the hit is greater than if you went slower, right? And so here's another example. So let's look at this picture here. And let's pretend that the detector is a wall, and that these units of energy are different material. So let's say the top one here is like a pillow, or, you know, a marshmallow, something really not very dense. And so if you took a kilogram of marshmallows and threw them against the wall, they might not damage the wall. But if you took a kilogram of uranium and threw it at a wall, it's going to maybe knock some particles out of the wall. So it's going to deliver more intensity to a smaller area of the wall in a shorter period of time, because it's going to be in a, you know, contained in a smaller area, you know, smaller region. So that's my analogy. Is, you know, when you throw a, you know, a kilogram chunk of lead at a wall, it's going to maybe break the wall. Whereas if you take a kilogram of a bag of feathers and throw it against the wall, it's going to hit the wall. It's going to hit a greater surface area in possibly a longer period of time. It might take a longer period of time for it to, you know, to completely bump into the wall, and it's not going to damage the wall necessarily. So that's the analogy here. So that's how I rectify how each wavelength can carry the same energy, but you're going to experience a greater intensity when it hits the wall. Does that make sense? We have
a question from Jack.
Sorry, what?
We have a question from Jack.
Okay, Jack.
Right. First of all, I want to congratulate you on one of the best presentations I've seen on these Saturday mornings.
Oh my God, thank you.
And without interruptions, I thought this is a great way to present them, because you got your entire theory across.
Great.
One of the major problems I see in physics is using scientists' names for things, and when unit analysis makes far more sense. We need to get rid of scientists' names and put in what you were doing. And I just want to say it's a great presentation. I'm going to spend quite a bit of time studying what you've done, because it makes I don't know whose that is.
Okay, I hope it's not me.
Okay.
Thank you, Jack. I really appreciate that.
I think I can fit in quite a bit of what you're doing and some theories that Dr. Philip Karnarev from Russia has. He doesn't, he changes Planck's constant to totally something different altogether. He doesn't use an H at all. He changes it into actual units like you're doing. Yep. And I want to take your unit thing, stick into his analysis. And so I feel like this is going to advance quite a bit of what I'm working on as well. So thank you very much.
I'll take it then that you're on my team. No, you know,
I will study your work.
I know that's what I mean. Like,
yes.
Yeah, I'm looking for team players, people that I can have a conversation with and not argue all the time, right? So thank you. I appreciate it.
You're welcome.
Okay, Harry's got a question.
Okay.
So have you made this, given this presentation to Dr. what was his name?
Dr. Neil Turok? Actually,
yes. Have you presented this to him, and what are his criticisms?
Okay, so he is kind of a tough nut to crack. That's a good question. I wrote a paper. The very first paper I wrote on this was called Calibrating the Universe and Why We Need to Do It. And I published that in a journal called Physics Essays, which is a Canadian journal out of Ottawa. And it took me 2 years to get that published, because obviously peer review, I mean, it's a peer reviewed journal. So I had to argue and argue and argue, and finally they couldn't argue my points anymore, and so they let it through. So I sent that paper to Dr. Neil Turok, and of course I never heard anything about it. So yeah, I've been trying to get through to these people, but I'm trying to be very patient as well, because okay, I don't have a PhD, and they don't like that. They don't like people like us, dissident thinkers that are trying to, they think we're trying to break physics, but really what I'm trying to do is I'm trying to fix it. It was broken when I found it, you know what I mean? And I'm trying to fix it. So I'm still trying to get through to
Lori,
him.
the key point is, I think, as you know, as you recognized right at the beginning, is to make contact with, let me just ask this question. Did you start going down this road as a result of going to his lecture? Is that what you're saying? That was my understanding of what you said.
No. This lecture was, well, when was it? Just a couple of years ago, but I was on this path long before that. I've been trying to get through to him. So I've, and I've actually met him a bunch of times. He comes to our university quite often, and I met him like in 2013 and talked to him. Like I had a nice conversation with him, more about my fractal cosmology, and he seemed interested. But then when I tried to follow up later, he would ignore me. So I went to this lecture, and actually if you go on YouTube, you'll find this lecture that I showed at the end there, and you'll see me at the end asking him a question, okay? And he, kind of, well, I don't want to be kind of mean. I want to stay on good terms with him, but he kind of snubbed my question a little. I asked him about the fractal nature of the universe, and he gave me a very, basically said, I don't know about fractals, blah, blah, blah. So anyways, these are tough.
That's a typical answer, so yeah, nothing real.
It's fine. Like, these are tough people to get through to. I understand their position. They get people all the time, sending them papers and, trying to, and I don't have a PhD, so I don't have a lot of clout. Although, if you look at my ResearchGate profile, you'll find that I've got a really good, my ResearchGate profile is pretty good. So I was hoping that maybe, so here's my ResearchGate. I'm in the, my ResearchGate score is higher than 85% of the people on ResearchGate. So I have a lot of papers, but through my work where, so that, and my papers, my personal papers that I've written, I've gotten a lot of attention from people, but not, people like him. So, I'm still working on it. I'm trying to be patient because I don't want to scare them away. I don't want to, timing is everything. So the timing has to be right, I think. Right? So.
Well, what you're offering is a different interpretation to the classical theory, if we want to call it that.
And that's all it is. It's just a reinterpretation. It doesn't change the, I'm going to call it, say, numerology. It doesn't change the numbers, okay? The number is Planck's constant.
I understand that, and that's difficult. That's a difficult idea to pitch when what they're doing. First off, a couple of comments about the lecture that you presented that he gave. I thought it was somewhat misleading.
Yep.
And I think you tried to point that out. There were like some misleading things. And a person who was sort of a layman who didn't really quite understand where he was making misleading conclusions would be, would accept that. And so that's pretty much what they do. And you have to, and it's kind of a hard road to, explain to people that, well, what he said or in there, his conclusion was misleading because his argument was misleading.
Exactly.
And then when you try to explain it, people can't follow what you're saying.
Right. And these people are looking up to these people, right, for, the secrets of the universe, right? They're looking, really looking up to these people. And, I did too for a long time. The Perimeter Institute, I don't know if you know about the Perimeter Institute in Waterloo, Ontario, Canada, is, it's a pretty famous institute. In fact, Stephen Hawking was a chair of the Perimeter Institute while, when he was living. And Neil Turok is, was good friends with, with Stephen Hawking. In fact, that picture that I show of me with him was the day after Stephen Hawking passed away. He gave a lecture at our university, and I went to that and got the picture. So, and he recognized me because we've met a few times. So, you know, it's just, I'm making little contacts here and there, and, you know, hopefully maybe, you know, because now that he recognizes me, maybe I can go a little further. Maybe he'll see this, you know, presentation and see where they went wrong, because I needed to go through the line of thinking from beginning to end, and that's why I did the presentation like this. I needed to show you guys my logic from beginning to end. I've been trying to do this through like the email groups and stuff, and it's always like a little piece here and a little piece there, and I get arguments all the time because they can't obviously read my mind. So now I just gave you my mind. I just let you read my mind, and so this is my logic. I think it's fairly solid. The logic is fairly solid.
Well, I like to point out one point here where I think there's a weak point in your argument.
Okay.
And that is the slide where you show E equal to the Planck constant, and then you have S and 1 over S.
Yeah, those are standard units. That's the standard way, like this one here.
Right. Now, I would argue that you've written that incorrectly. It should be S times S to the -1. And then your argument falls apart.
It's the same thing. S to the -1 is 1 over S.
No,
so
it's not. No, it's not. That's
sure?
the point.
Okay.
The point is that frequency is the inverse, and the inverse is defined as the reciprocal with respect to the unit.
Right.
Okay, which is 1. And they can argue that your interpretation of that is incorrect because it's the reciprocal. It means the frequency is a reciprocal of time. The unit doesn't enter into it.
Yeah, okay. I can buy that. I can buy that.
You understand what I'm saying? That's if I was gonna.
Yep.
Here's what I'm saying. If I was a physicist like Dr. Turok and I was gonna find a way to object to what you're saying, that's one place I would focus.
Okay. But this is how I've seen it written as well. So, you know, like, so.
I'm just commenting on that, Laurie, so you know. Generally, I thought it was pretty good. I have long thought that energy, the E thing, is a somewhat mistaken because power is the fundamental and not the energy.
Yeah, I think that's the most important point of my regardless of whether what someone just said is, you know, about the inverse of S. Really, what I want to write is this power equation. And then everything, then I don't even need modified unit analysis, to be totally honest, if I can write it in terms of power. It makes more sense to me.
Yes, I understand that. And I agree 100%. That's kind of, you know, I came to this conclusion many years ago that power is the fundamental. But the physicists have focused on energy as being the fundamental.
Right.
And that's even going back further than Planck. That goes back to Joule and
but you know what's ironic? Okay, what's ironic is that we have a unit for force called the Newton. Okay, so force is momentum per second. Okay, so force is like a fundamental, right? So like we have a unit for force, but we don't have a unit for momentum, right? So you know what I'm saying? So yeah, so there's a lot of inconsistencies in the way physics is done. It's not as rigorous as I would like it to be.
Well, it's not as rigorous as they think it is, I would think.
Right, exactly.
So the part of the problem has, you know, you brought that up. It's this idea that force is the fundamental. Yeah. That's kind of a problem. And it's difficult to get away from that because that goes back to Newton. And that's sort of saying that Newton is wrong. And no physicist really wants to say that and go on record as saying that.
It's not about being right or wrong. It's about being rigorous or not rigorous, right? So most of the problems I have are about the language and not about the physics. right? I have a problem with the language because if you do unit analysis wrong, you're going to get a wrong interpretation. So it's not even about the physics, it's more about anyone being right or wrong. It's just about whether it's rigorous enough to get a proper interpretation, right?
Okay, so Jonathan Powers has a question.
All right.
Go ahead, Jonathan.
Hey, excellent presentation. I was just wondering if you had ever heard of a man, Pierre-Marie Robitaille. He's a radiologist who did a lot of MRI work, and he has discovered that Kirchoff's law of thermal emission is incorrect, which is very closely related to Blackbody experiments. So if you hadn't heard of him, his last name is Robitaille, Robitaille, and Pierre-Marie is his first name. I think a lot of stuff that you said seems right up the alley of the talks that I've listened to with him. So I just wanted to let you know that.
Thank you. Yeah, I will look him up.
Yeah, he's kind of criticizes this whole Planck Blackbody radiation law, the Blackbody radiation law, as I understand it. And there was a presentation given a couple of years ago that probably got lost in the transition from NPA to CNPS. Does anybody remember seeing that presentation?
I wonder if it's up on YouTube.
I'm not sure who gave that presentation.
Well, it looks like Jack has got another question here. Oh, by the way, I put a link to this paper, the Planck's constant nature of light, in the chat. That is available on ResearchGate. And if you want to find Lori's papers, they're right there. Just search for her name, and you'll see that she has got lots of papers. So go ahead, Jack.
Again, Professor Konorev has shown that one of Newton's laws of motion is incorrect, and he's rewritten it with 4 new laws. So Newton wasn't correct either fully. And I've already printed out her Planck's constant of nature of light. I intend to study it over the holidays. Again, I'll be getting in touch with you, Laurie. Because
yeah, you can get in touch with me directly. And my email is on my papers, so you can contact me directly for sure.
And anyway, thank you.
You're welcome.
So one question I have is this really getting down to the nature of light as to whether it's a particle or a wave? Because I think your analysis is pretty clear, and I totally agree with that, you know, what it means per cycle. But from the people who are in the light is a particle camp, you know, they would just say that, yeah, that the Planck's constant amount of energy is just coming in like a bullet, and there are just more bullets per unit time. That's creating the observed power. Mm-hmm. So that's certainly one valid way of seeing it versus like a very, very long wave. Like one of the objections is like, you know, how can we have like, you know, a bullet that's like a mile long? So if you're talking about a very long wavelength, you know, how can that thing be like a mile long versus there just being one bullet in that length of mile? So what do you think of that?
Okay, so there's a lot of possibilities. So I'm open to a bunch of possibilities. Like I said in my intro, is light, is it a particle? Is it a wave? Is it something completely different? So one line of thinking that I'm entertaining is that, and I get this from the electric universe, is that it's more like an electrical signal. So it's more like a voltage, right? It's more like a voltage change over time. And so then amplitude would be the voltage. And so what I found interesting is when I wrote the units, so you can see my screen, right?
Yes.
When I wrote the units in terms of power and then wrote my units like in modified unit analysis, right, where I put the delta terms in, I noticed it looked very similar to the power equation for in electronics of voltage times current. Okay, joules per coulomb, coulombs per second, joules per per cycle, cycles per second. They both amount to joules. So I'm now entertaining the idea that light is a like I'm modeling light as an LC circuit, okay, just to see what this buys me. And so I was able to write an equation. So this is for light. Okay, I was able to write an equation for capacitance, and that's permittivity. Okay, I was able to write an equation for inductance, and that's permeability, and then reactance, voltage, current. I was able to deduce, and notice that these are all in the frequency domain. I like doing things in the frequency domain. It's kind of like modeling what MRI physics does. They convert everything to the frequency domain, and then they convert back to, the spatial domain. So we could convert back to wavelength if we want. If I do everything in the frequency domain, I can convert back to wavelength if I want. But I'm not sure wavelength necessarily has to have any meaning, physical meaning, right? Because it could just be, if it's the particle model, then wavelength is just the space between particles. It's, so then you don't have the wave, you just have the particles. So I could support the particle model, I could support the wave model, and I think I could support this, that light is more like a electrical signal. Or, it could be, it's analogous to, it might not be exactly. So there's a lot of possibilities, and mine doesn't, all of them kind of work with this model. So everyone can be right almost when you do it this way. So
okay, you're not good, because I think that's one of the biggest controversies, especially when you're discussing that with that professor, that he clearly thinks that light is a particle.
He said it out loud. Yes.
Yeah, he said it out loud.
Yeah.
So, but then there's people like me who would argue violently that it's a wave and it's not anything like a particle. But
yeah,
I think this kind of unit analysis can actually work both ways and really say one way or the other, whether it's a photon per se, or is it just a wave like sound?
Yeah, but he also thinks that this is the energy of a photon, of a fundamental particle, but this is a variable. So this has, this is what really bothered me about the whole thing, is that, when I go to Wikipedia and type in photon, it says photon is a fundamental particle. But how can it be a fundamental particle if it's a variable? This is fundamental. H doesn't change. It's the fundamental. This can't be fundamental. So that bothered me like forever, and then, which is another reason why I went down this path to try to figure out, because I want to understand the universe. I want to understand light. I need to. I really, really do. So this really bothered me, that this is a variable. So how can it be fundamental? It doesn't make any sense.
I think the issue, Lori, is that over time, what physicists have been saying has sort of changed. And the modern, what people say today is kind of evolved over a period of time, and it's not the same as like Planck would have said it. And, Planck said that the photon didn't exist, that the quantum of energy had to do with the interaction in the atom. And so he would have said that there is no photon of light. But, the modern people have sort of gotten on the bandwagon of Einstein, and since Einstein is sort of their hero, if they can connect their current belief to something that Einstein said, then they, can sort of justify believing that. And that's what's kind of happened. And today, you see people talking about photons with respect to radio waves. And, every time I see that, it's sort of, how can you talk about a photon of a radio wave? It's a completely alien concept to an electrical engineer. We don't even need that concept.
Right. Okay. And that's why I'm leaning towards the idea of light actually being more of an electrical signal, because that would make more sense for radio waves, right? And then you could think of the electron, you could think of it as an antenna, and you have to vibrate the electron at just the right frequency in order for the electron antenna inside the atom to, jump up a level. So I haven't fully finished this line of thinking. So this is sort of future work. This is where I'm going because, you know, my logic supports this idea. And I think that this idea might be able to bridge the gap. So it's not, you know, light isn't a particle and it's not even a wave. It's an electrical signal, right? And, but then in order to have an electrical signal, you have to have a circuit, right? So that's where, you know, my model of the ether comes in. I don't really want to get into it now, but I think everyone knows that I support this, you know, that the ether is at least filled with electron-positron pairs, which would give them, you know, which are polarizable, which would give maybe a mechanism for this, you know, electrical signal. So, but, you know, I don't want to go down that path right now. In the future, maybe I'll give another talk about that once I've outlined it more thoroughly.
Now we have some comments in the group chat here.
Okay.
There's Planck who's saying that, you know, the problem is that we measure gamma rays as the smallest wavelength and greatest frequency, and this is a measure of a photon from a concept point of view. So I can kind of see that, because when you do annihilation, you know, you get these like two very, very neat gamma rays that go off back to back, and they can detect them in these detectors. Yep. So those kind of look a lot like a particle from that standpoint, in that they're very isolated. They only show up as two spots on the walls of the detector, but they do have, say, a measurable frequency. And yep. The only things that can have frequency are waves. So if those were actually bullets, then it would have no measurable frequency, in my opinion.
Well, I can have a machine gun, right? And I could shoot a whole bunch of bullets, and that's going to have a frequency. So frequency isn't just about waves. You can have frequency of flow. So this could be a flow. You can have frequency of flow, right? Where you're counting the number of particles that are going past you. So, you know, frequency isn't just about one thing. Frequency could be frequency of wave. It could be a frequency of, like in an electric circuit, frequency might be the frequency of number of coulombs going past a point in space in time. So, well,
I suppose the gamma ray experiment there depends on what are the number of things that are going past.
Right.
So in the case of positron electron annihilation, they're thinking there's only like one thing going by. So in that case, then the one thing would have to contain the frequency, I would suppose. But
well,
that would be
exactly. In order to have frequency, like if it's a particle model, and in order to have frequency, you have to have at least two, right?
Yeah, at least two. If you're a wave, you need just one cycle.
Exactly. So, yeah, but how can you tell when something hits a detector? How can you tell if it's one or two cycles or 1 second worth, right? So, so this model here would be like, if it's a wave or if it's an electrical signal, think of this as a changing voltage, right? Then you could also just have one cycle, and that would generate the power. Let me put this back up, right? That would generate the power. So that would be like this. So I really think it's interesting that these two, when you rewrite Planck's energy equation in terms of power, you get something that looks really similar to, you know, the power equation of a electronic circuit.
Well, I think the similarity might just be due to the fundamental quantization. Probably anything quantized over time would probably be exactly the same kind of analysis.
Yeah.
I'm not sure that saying that it's even related might be taking things a bit far.
Well, I like to use the word analogous, right? Because it's an analogy. So I love analogies because you know, being a fractal cosmologist, right? Actually I use the word self-similarity instead of an analogy, or I use them, you know, one the same as the other. So I like this idea of self-similarity. So something that happens at one scale can happen at another scale, or something that happens in one domain, like the domain of electronics, could happen in the domain of light. So so that's what I'm always looking for, analogies and self-similarities, because I would like to have sort of one law of physics but then scale the law of physics to different scales and different situations. So the equation would be almost exactly the same, only what you're changing is the domain. So you're changing, so instead of the domain of cycle, it's the domain of Coulomb. And that's why in modified unit analysis, I use the term domain, right? Because a domain is something very specific. You know, the domain of time is not the same as the domain of space. They're orthogonal. They're nothing like each other, right? But they can, you know, time and space can, you know, have a relationship. So modified unit analysis, actually unit analysis is what you're looking at are the relationships between the domains. So
okay,
when
Jim, I've got some more notes in the chat here.
Okay.
So Jim notes that radio waves.
Bill Lucas has a question. He's raised.
Yes, he does, and I will get to Bill after this. So just hang on there, Bill. So, but he says, note that radio waves can be generated at any energy for a given wavelength. E equals HF does not apply. So Jim is saying that E equals HF only applies to, say, visible light and not radio waves. Do you have an opinion on that?
I'm pretty sure that's not true. I'm pretty sure that's not true, because I think I could have a signal. Here's a little graphic. I think I sent it to some people a while back. It's kind of showing, so there's the Earth, there's the moon, and the, you know, light travels 300,000 kilometers in 1 second. So in one, if I emitted a radio wave, whatever that is, it would get to this point here in 1 second. So it wouldn't quite make it to the moon. So if it's a wave, then this is 1 hertz, okay? So if I plug this into E, you know, E equals HF, I'm gonna get H. So 1 hertz plugged into this equation, if I plug in 1, I'm gonna get H, okay? So 1, or if I have 2, it'll be 2 times H. So whatever frequency, so I'm pretty sure that this would be considered a radio wave, right? If I had a wave that went from here to practically the moon, that would be, you know, considered a radio wave, and that would, this equation would apply to it. So maybe they don't need that equation to do radio physics, but
you froze time when you drew that picture.
Yep, I was, yes, I did.
So and you have to be careful about
this is
what
just
your definitions mean, and this is the problem where space and time, you have the duality of space and time when you're talking about this
right.
topic of waves, and you can't really define a radio wave like a picture like that. You can define that as being the wave at a fixed point in time, or you can define it as the energy passing a fixed point. Okay.
Yeah.
And
this
then
is
do
okay.
it in the time domain. So you have to be.
This is just a schematic.
Confused.
Okay. No, but you have to be very careful. I'm not drawing. This is just a schematic. Okay. This is a schematic so that I can talk about, you know, the speed of light and how far light travels. And like, if I was sending a continuous signal to the moon, after 1 second, let's say I didn't stop. I'm continuously sending a 2 hertz signal from the Earth in this picture. And if I could take a snapshot of it after 1 second, right? Because I would see this picture. So it's just a schematic so I can have a discussion, and I don't think this is what light looks like necessarily. And obviously it's not an animation, so I can't, you know, I can only show time, you know, so in 1 second, the wave would get to here. So really don't read too much into the way I drew the picture.
Now, Jim, he has another comment here.
I would like to hear from Bill Lucas.
Okay, why don't you go ahead, Bill, and but I want to get back to what Jim was talking about here.
Okay.
Well, I just had a comment about the whether light is a particle or a wave.
All right.
When Einstein's wife did the experiment, the photoelectric effect, she did it on a crystalline form of a metal, and you get electrons emitted from the absorption of the energy. And it gave the idea that light was a particle in that sense. But when they did the same experiment on the same metal, but in a non-crystalline form, there's no photoelectric effect.
Okay.
And then when we started making optical circuits for computers and things like that, for chips and things, we discovered that you have to make a small microscopic antenna to receive the signal. If you just leave non-crystalline forms of the material inside the optical circuit, you don't get any signal transmitted. Right. So it looks like there's a wavelength associated with the motion of light, and that seems to agree more with the wave notion of light than a particle.
Okay, so here's my take on that. Okay, so in a crystalline structure is going to have a resonant frequency. It's going to have a natural resonant frequency. Okay, so let's say this is the crystal here, and these particles are coming in at the correct resonant frequency. So the analogy I have for this is pushing a child on the swing. Okay, if because I have kids and grandkids, and so I've done this a lot. When you push a child on a swing, you have to push it at just the right time to get it to go higher and higher and higher. And if you keep going, except gravity kind of prevents this, but if you keep going, eventually the kid's going to fall off the swing, right? Because you're going to go so high that they're going to lose, So that's how I see the photoelectric effect is you're hitting the electrons at the resonant frequency of the crystal, and eventually it just knocks them right out. So that could be particle and that could be wave. Either way would be fine with me.
Well,
you know what I'm saying?
Yeah, I understand what you're saying, but in the optical circuits, they have to make an actual antenna to receive the light, and just the crystalline form has built-in antennas also for particular frequencies, and so it's I don't know. It seems to me that there's a lot of evidence for light not being so much of a particle as a continuous wave.
Yeah, and I'm happy with either interpretation. Actually, at this point, I'm not going to decide because I'm still entertaining this electrical signal, which would be wave-like, because like a voltage is wave-like, but it maybe the wave isn't in physical space. Like in the voltage, where's the voltage? The voltage, we draw a voltage like this, we draw the voltage like this, but it's not. It doesn't take up physical space. So it could be all of the above. It could be a particle, it could be a wave, and it could be electric signal. And they all, support this kind of picture.
Michael Antesky.
Sorry, what?
Michael Antesky has a question?
I'm an adherent of the ether theory, and I have my own ether model. And to me, it's hard to use quantum mechanics and mathematics and quantum dynamics to explain the propagation of light from an energy source, unless there's an ether interaction between the quantum forces and the underlying ether, which I think is a vibrational force. And this goes back to first causal theory, which is that originally there was a universal oscillation which transitioned to a universal vibration, and that there's an underlying vibrational dynamic process in the ether, and that the photon is built up of these universal elemental units from the beginning of the universe, or of beginning of everything, the universal oscillation. And then if the photon is built up of these more fundamental elemental units, a photon would not be a solid particle. It would be a particle capacity, and photons would be generated and being dissipated all along the course of a light beam coming from some energy source. And to me, it's more conceptually understandable with this kind of a model, instead of sticking with quantum mechanics completely.
Right. Yep, no, I agree. And if you want to see my take on the ether, which I call the medium for the propagation of light, you can find this paper on ResearchGate. Basically, in this paper, I show the logic of how the equation for the speed of sound can be used to deduce the fact that the ether consists of electron-positron pairs, and they would be like mini dipoles. They would be polarizable, but there is definitely an ether. And with these electron-positron pairs, you can have either, if it's a medium, so it can be a wave. Okay, there's a medium, so as soon as you have a medium, it can be a wave. And I'm more partial to the wave interpretation of light than I am to the particle interpretation of light. So I agree with you that it is more likely a wave and less likely a particle, but it might also be kind of like an electrical circuit. So I haven't rolled that one out yet. But you can look and see my logic here. I basically outline why there should be a medium and what it's made of. And I show the similarities between light and sound because I'm in the field of ultrasound, 3D ultrasound, and so I'm more familiar with how sound waves travel through various different mediums, including, especially the tissue of your body, right, and what the speed of sound of that is, and how ultrasound. So I'm more interested in ultrasound than air sound, and we're talking about sound waves through a solid medium or a liquid medium or some medium. So so I'm more interested because these waves, because of propagation, I believe it's a wave and not a particle. So I'm more leaning towards it being a wave and not a particle because of propagation.
If I could interrupt just a second,
Yep.
I think another thing to look at is quantum entanglement, because if there is a vibrational ether dynamics going on, it would be linear, and really there's no other way to explain quantum entanglement unless you have a linear process going on with a matrix, which is also composed of elemental units which behave linearly, which would be a vibrational type of dynamics.
Mm-hmm. Yep. So here's a picture. You can still see the screen, right? So here's a picture. I actually got this from Don. I stole this from Don Hotson's paper, where you can kind of see if the ether is made of electron-positron pairs, that they could, when you have like a positive charge and a negative charge, they would align in the pattern that you see for charged particles, right? If you have a negative and a negative, then you see that they would line up. So this actually gives a physical mechanism for the electric field, right? And so I like this model of, and these would also be the medium for the propagation of light. Light would propagate from here to here along these paths. So that's basically where I'm going with my ether model.
So I noticed, Jim, you still have some more comments in the group chat. Did you want to ask Lori a question directly? Jim? Or maybe Jim is shy.
Hello? Hello, can you hear me?
We can hear you.
Yeah, your statement about waves having only an energy equals HF, and I was trying to say with when you're transmitting EM radiation, you can have any amplitude based on the power of your transmitter.
Right, and then what you're doing is you're stacking. You're sending more energy units. You're sending more energy units per unit time. So you're you're stacking them when you do that.
It still comes out as one wave.
Yeah, I'm not sure. I mean, I think the the engineering point would be that if you have a radio transmitter and you send a single cycle with 1 watt of power, and you can receive that in your receiver and measure how much you get, you can send with 2 watts of power, and your receiver will receive twice as much energy with exactly that same wave. And the only way that could possibly be is if the wave has a much larger and variable amplitude. So I think the point being is that that would contradict this formula E equals HF, where if there is an amplitude, that must be a constant.
It's not amp. It's not amp. Yeah, it's
not. This is another example saying that the amplitude must be variable, right?
Yeah, but this isn't. This doesn't correspond to amplitude. This is not amplitude. I know I'm drawing it like that, right?
Well, amplitude. Amplitude converts to energy and power.
This is the footprint, right? This is the footprint of the wave, and you can stack them. So I can put more. Yeah, they're going to be in phase. They better be in phase, right? I can stack them. So I can put 2 of them here, and you're going to get 2 of them here, and yeah, you're going to get twice as much energy. Obviously, in this detector, you're going to receive more energy units because you're stacking them. So that's how I see it. I don't know if I'm right. I'm not saying I'm right. Okay. I don't, this is just a logical argument. And to address what you said, I would say that then you're sending 2, you're stacking them because, waves can stack. So, right. So then you're kind of sending 2 of these in one, but the footprint of the wave is going to stay the same. You're just going to superimpose 2 of them, and you're going to get 2 of them at the same time, and you're going to detect twice the power.
Well, it may be true.
Last week, we had Bob Gray. I don't think he's with us this week, but his conundrum out of this is to treat radio waves differently from light waves. So that I suggest that might be one way out of this, rather than saying that they stack or anything like that. Because I think in a radio transmitter, you can probably quite clearly see that there's nothing being stacked when you transmit a 1 watt signal versus a 2 watt signal, especially over a single cycle. But that
the theory of a laser says that they're stacked. I mean, you
exactly.
could say that.
Exactly. It's like a laser. Exactly.
And the missing word that you're missing is there's a coherency of
right. Coherency.
all of these.
Yep. You're creating a coherency.
I think that wasn't Bob's point at all. His point was that waves, electromagnetic waves generated by radio methods, which is basically shoving electricity into a wire, that can happen at any amplitude versus light, visible light, which is what Planck's constant is based off. All of those experiments are based off of generally light generated by atomic processes coming off of atoms being excited, and all that is based on electron transitions. And,
okay. Yep. There could be a difference. Yep. There could be a difference between
there could be a
light.
Difference there.
Mm-hmm. Yep. Absolutely. Yeah. No, I can see what you're saying. So, so light that comes from transitions of electrons in an atom might be different than electrons in a metal, right? In a metal that are waving, so they're kind of waving the ether maybe and creating a wave in the ether that way. But either way, but here's how I see it. In the atom, when the electron jumps up and down the levels, and if the electron is coupling to a medium. Sorry, what?
Yes.
Somebody's talking.
I think that was some side conversation. Go ahead.
Oh, yeah. So technically, okay, so if there's an ether and the electrons are coupled to the ether like this, so here, let's say that's an electron, it's coupled to the ether. When the electron wiggles, it's going to wiggle the ether, and it's going to create a perturbation, a field perturbation, which is going to manifest as a wave. So even when an atom is transitioning inside of an atom, it's wiggling the ether. So they could both still be the same thing. Except that with the radio waves, you have more control over how you stack the waves to create a bigger amplitude.
Yeah, I would be kind of curious to see whether they could accomplish anything like the photoelectric effect, but using a radio wave. So I don't think they have, and that may be due to this.
Oh, you know what? There is an experiment that they're doing at work, where I work. Okay, they're taking radio waves, RF frequencies, and they're focusing them and into human tissue, and they're getting them to create ultrasound waves in the tissue. So it's not exactly what you said, but we're taking radio waves and creating sound waves in the body, and they're able to image the liver. Okay, they're using this to image the liver to determine the fatty tissue in the liver. So they're converting radio waves to ultrasound waves, and that is really cool. That is really cool. So I don't probably doesn't answer the question, but it's an interesting way. You know, radio waves can be converted to sound waves, and that's really neat.
So Michael's got another question for you.
Well, her statement that perturbation of an electron would cause a wiggling in the ether would be contradicted in my ether model, which is that there are two kinds of dynamics. You have quantum dynamics, fields, waves, vectors, and so on. And then you have this other completely different dynamic, which is a vibrational dynamic, which is, as I submit, is the only way you can explain quantum entanglement is with a vibrational ether. So this wiggling of the ether would not occur because it's a different dynamics.
Great. Well, you know, when people say it's the only way, I become really suspicious, because Neil Turok said the only way we can explain why the sun doesn't completely dissipate is if you know, if the photon is a particle, and that, so you can't really say it's the only way. I object to anyone that says that. Maybe it's one way. There might be. It's very misleading. There might be another way. I have a different approach to entanglement. I'm not going to talk about it now, but it has to do with my ether model, where there's 3 ethers. There's primary, secondary, and tertiary, but I'm not going to get into that now. But you can't really say it's the only way. It's a way. I'm sure that it's a way, but it's not the only way. So
my comment about what Jim is saying is that in the filament of a light bulb, supposedly the actions of the atoms that are emitting light, assuming that that's a correct thesis, are incoherent, and but in a laser they're coherent. But in a radio transmitter, you don't have emissions on different frequencies. You transmit basically on one frequency, and the mechanism that is used to produce the signal is really not the same thing as what's going on in an atom, at least from what we understand. So I don't really see this as being a particularly devastating argument.
Right. No, okay.
But I can understand how you could say that it's the same thing as stacking. The issue in my mind, this is kind of how I see it. I think you have to sort of define what you mean by particle and what you mean by wave pretty precisely before you even entertain making an argument that light is a wave or light is a particle. You have to really define what those concepts mean. And I think once you try to do that, you'll find out that that gets you into philosophical issues and mathematical issues and semantic problems. So, basically, I think what most people do is they resolve it by deciding it's one or the other. And
yep.
Arbitrarily.
So there's an echo going on. I'm a big fan of the particles of the universe theory by Jeff Yee, where everything is a wave. And so particles are standing waves. And so that, that could be a good resolution of, everything's a wave, just particle is a standing wave. And then you could do everything with wave dynamics and not worry so much about what's a particle and what's a wave. You just talk about standing waves and traveling waves, and that's it. And that's a beautiful solution. I don't know if Jeff is still on the line, but anyway, so, okay, good. So I'm a big fan of your theory, obviously, but I think it can also resolve a lot of these arguments about particle, wave, is it this, is it that? Standing waves and traveling waves, that's all there is. Transverse waves and longitudinal waves, that's it. So the universe is kind of binary in that way. And it simplifies things quite a bit, I think, when you do it that way.
Yeah, but don't you think that somebody who insists on constructing everything out of particles could do an equally convincing job?
Then they have to explain waves.
Well, they do that by saying that there's just a progression of particles emitted. You know, Roger Ryden, you know, pretty much presents that point of view.
Right.
And
I am not against any, if a particle model can explain everything, then I'm not against it, for sure.
Yeah,
I'm not, obviously I'm not claiming to be explaining everything. I'm only just explaining this one little thing in this presentation.
well, my comment, Laurie, is that I think it's a sort of a trap, an intellectual trap, to sort of say everything should be constructed out of waves, or everything should be constructed out, to pick one or the other. I think that's kind of where we're trapping ourselves and what physics is. And I think that that's a misleading kind of type of argument.
You're saying I'm being misleading, because all along I've been saying it might be a particle, it might be a wave, it might be an electronic signal.
What I'm saying is that to try to insist that it's one or the other, and to make it a strict dichotomy is
I'm not doing that. So I'm not doing that, right? You admit that I'm not doing that.
I got that. I'm not accusing you of that.
So we don't need to talk about that anymore, because obviously I'm not doing that. So we don't need to point fingers at other people, because other people are doing that, but we're talking about what I'm talking about right now.
Okay, so it looks like we're getting towards the end of our time here. So let's see, I have some last comments here. So Laurie, you started out your presentation on the nature of light, and you started out with the two equations, E equals mc squared and E equals hf. And I really liked how you showed that those two things really aren't equivalent, because I really have just a sneaking suspicion that this is what goes on in physics all the time. And a lot of nonsense because of that. People are equating apples and oranges and coming up with complete nonsense. So you started out your presentation with that, and I thought that was interesting. But you know, as you're still sitting on the fence of whether, you know, we're really talking about particles or waves. I think so. You're talking more of a analysis on what those things really mean. They could still mean separate bullet packets that have quantized energy, or it could be a wave with a certain fixed amplitude or something. In either case, I think it's important that your analysis shows that this E equals hf is the power delivered over 1 second, and not anything having to do with, say, a photon. You know, this is energy delivered over 1 second is what it literally says, and that the smallest amount of energy is the Planck's constant, which I think is one of your main points. I agree with that totally.
Excellent.
And any other interpretation is just, I don't know, wrong. But
yay! it's the bug. Okay, yes. I'm gonna tell you about this picture, because this is me. This is me. When I was younger, I was in a children's theater troupe, and I was the bug. So that's why I did that. I was just me being funny. So I hope that wasn't
too annoying.
Hope it wasn't too annoying.
No, that was very cute.
Thanks.
So yeah, a lot of your presentation is about just that main point, which I think is not a very complicated point.
Exactly.
But you still have this whole controversy over whether the actual nature of light, as to whether it's like a bullet that's just coming in at a certain frequency and the wavelength is just an amount of space between it, or whether there's actually a wave, in which case there must be some sort of medium which is compressing and rarefying at these rates. So, we presented a lot of different papers in the last couple of weeks. We had Ian Cohen, presented a paper basically saying that the physics, like the equations between light and waves, is fairly similar. And I guess that would be more favoring a wave thing, since we can't find anything which is radically, irreparably different. And then I presented my other paper, which was just simply just being completely biased and just saying light is completely a wave, and just seeing where you can go with that. And then we have your paper here, which indicates more about the meaning of these equations, about like what Planck's constant is. So I think that gives us a lot of things to think about. But I think at some point, probably only experiments will probably tell the difference, because a lot of people, the people who think that light is a photon, literally a particle, it's not like their theories don't make sense. Right. They can explain absolutely everything, as well as anybody who could explain them as just like a wave. And everybody has to explain all these things, and it's kind of, but I think ultimately an experiment would have to show either the existence of a new particle, which we would call a photon, which could be experimentally shown to have Planck's constant in it, right. Or the alternative would be the wave people would have to show that there's actually a medium. So, for like you and me, you have to actually experimentally find the positron electron C. Right. Exactly. So what we really need to do is convince someone to do one or two of those experiments, I think, maybe, to try and get to the bottom of this medium for propagation of light, because otherwise it's all just a bunch of talk, I think. Really? Exactly. That's the problem. We need an idea. We need an experiment. I work in the field of medical imaging, and I have access to tools and things. So if anyone can think of an experiment, I might be able to do it. Right? Yep. Okay. So I'll join your army, Laurie. Okay. Yay, you're on my team. Good. I always knew you were on my team when you gave your talk at CMPS, not last year, but the year before, and you were talking about electron-positron pairs, or electrons and positrons. Yeah, I was really happy about that. Okay. Well, thank you for giving us your presentation. Well, thanks for having me, and thanks for, being patient and asking great questions. I really enjoyed this. This was really fun. That was innovative that you presented your presentation already pre-made like that. We just had to get through the audio problems. Yep. So if you could cut that part out, I don't know if you can, but. No, I'm afraid I can't edit. It's just. Oh, okay. It is what it is. Okay, fine. No problem. Posted on YouTube shortly. All right. So, you can tell all your friends about it. I will. You can get thousands of views on our website. Wow. Over on YouTube. So just search for CNPS or John Chappell on YouTube, and you can find our channel, and you can see all the months and months and months worth of discussion we've had over the past year or so. All right, I'll do that. All right, so that will do it for this episode of the John Chappell Science Chat. I believe we do have Jeff here. Jeff, I believe, will be presenting January 12th. Oh, good. So don't miss that. All right. All right. Well, thanks a lot, and Merry Christmas, Happy New Year to everyone. Hope you have a good one, and be careful,